number of not so familiar faces. So welcome. It's sort of a stifling, humid morning out there, but it's going to be wonderful in this room. We are kind of here this morning for Hope Duke's honors thesis presentation. And let me give you a little sense of how this is going to go down. So I'm going to introduce Hope. Hopefully it will be memorable. And then we will proceed to the important part, and that's Hope's presentation on the research she's conducted over the last year. She's probably going to talk around 40 minutes, and then at that point we'll turn the lights back on and we'll open things up for questions. So if you're in the audience and you've got questions, that is a great time to ask her. And once that has sort of run its course, Hope will get to spend a little quality time with her thesis committee after that. We'll probably have a few more questions. And when that's all done, we'll sort of release Hope, and then we'll chat about Hope behind her back, and then we will go bring her back, and that's how it's going to proceed today. So this is kind of an annual tradition in the geology department, and Hope is the leadoff hitter for all of our presentations this spring. So we are, hey Caroline, that's my seat. What are you doing? Muffins are over there. So you stand up here and your seat gets taken. It's terrible. All right, so Gabe, can you flip the lights off?
The door closed as well.
That'd be good. So I'd like to introduce Hope. And it turns out I had the great pleasure of getting to know Hope really very soon after she arrived here at William & Mary. So here's a photograph in this exact class. In fact, I can kind of remember it right now. Hope was right here, yeah? Very first day of College 100. And you can already tell she's a very attentive student, right? Collaborating, working well with her partner in crime, Emily, right there. And they all look so young and bright-eyed in that photo. But Hope very quickly took to weather, climate change, the earth sciences, and really right off the bat became an important member of our community. She was so stoked up about this, she chose to go on our Geology 310 trip out west after her first year at William & Mary. And here you can get a sense of her teaming up with her mates in front of, this is Mexican Hat, Utah. And I'm not sure what was going on there with the field books, but anyway, it all looks on the up and up there. So she's always been game for sort of being in the field and being part of the things that we do studying the earth here at William & Mary. In fact, so much so, she decided to go back for round 2 of Geology 310. This was in Norway in the spring of 2017. If you actually can't locate Hope here, I've got, yeah, and I think she was kind of returning to her ancestral homeland in the Arctic there. And this is, I've never quite seen that look from her before. But as long as we keep her in the mid-latitudes, everything is fine. Hope has done a variety of research. She has really, I think, taken good advantage of her time here at William & Mary. Between her sophomore and junior year, she actually worked with Kelvin Ramsey, who's here in the back, and the Delaware Geological Survey, and really tackled a project thinking about sediment distribution and mollusks in the Atlantic offshore. But she joined the structure group, and we're excited that she's part of this. So I have gotten to travel lots of places, as Hope is going to regale you. We went to Austin, Texas to do science this past summer, and you can see here we are talking about the science after a long, long day. So I'm going to turn it over to Hope here in a minute. But Hope's project has involved a variety of things, from field work in the sort of backwoods of Virginia to sort of shooting up zircons, as you'll learn, in laboratories at the University of Texas. And her results are really quite fascinating. So let's welcome Hope to the stage, and I'll get her presentation queued up.
Thank you so much, everyone, for joining me this Friday morning as I share the results of my senior research in the Goochland Terrane in central Virginia. This here is a photo of me and my colleagues examining an outcrop of the state farm gneiss, which you will learn about in just a few moments. Here we have a generalized terrain map of the state of Virginia. So Virginia is comprised of many terrains, some of which are known to be of Laurentian in origin, such as the Blue Ridge Terrane to the west, and some of which are known to be exotic, like the Carolina Terrane in south central Virginia. And my research falls in the Goochland Terrane, which is right here in this study area. The Goochland Terrane has a complex and enigmatic history. So here's a generalized stratigraphy of the Goochland Terrane. These units were first mapped by Poland in 1976, and I'll start by walking you through the basement rocks and then the cover sequence. So in the basement rocks, we have the State Farm gneiss, which is a 1 billion-year-old granitoid gneiss. We also have the Montpelier anorthosite, which is a 1 billion-year-old massive. in the Goochland Terrane, and then a series of A-type granites that intruded the State Farm gneiss around 630 million years ago. And as we move into the cover sequence, we have the Maiden's gneiss group, which is a heterogeneous suite of gneiss, and then also lenses of the Sabbat and Fibolite within it. And the contact between the cover sequence and basement has often been interpreted to be an unconformity. The first modern work in the Goochland Terrane was done by Stuart Farrar in 1984, and he put together this map of the terrain. And he first noticed these three domes of the State Farm gneiss, the first, the second, and the third up here, and they're all flanked by the Sabbat and Fibolite. And Farrar interprets the Goochland Terrane to be of Laurentian origin due to the Mesoproterozoic age of the State Farm gneiss, the similarities between the Montpelier anorthosite and the Roseland anorthosite that's found in the Blue Ridge, and then also the presence of a granulite glaciers mineral assemblage throughout the terrain that's been overprinted by amphibolites glaciers. In 1989, Glover came along and put together a model for terrain accretion in the Goochland Terrane. And so here in this model, we have that Gondwanan crust was thrust over top of Laurentian crust during the Taconian orogeny, and then subsequent thrusting during the Alleghanian orogeny, and placed some of this Laurentian crust, where we have the Goochland Terrane, over top of the Gondwanan crust. So here we have the Chapawamsik zone, or the Chapawamsik terrain, and then the Spotsylvania high strain zone, which they interpret to be a thrust fault, and then the Laurentian Goochland Terrane. But not all researchers agree that the Goochland Terrane is actually of Laurentian origin. So in 2004, Bailey and others came along and they did a strain of vorticity analysis in the Spotsylvania high strain zone, and they found that the Goochland Terrane experienced at least 300 kilometers of dextral displacement during the Alleghanian orogeny. So if we were to trace the Goochland Terrane back to where it was before the orogeny, it would place it in New England up here in the Northeast. In addition to the strain analysis, they also observed that there are not many links between the adjacent Blue Ridge terrains that we observed and the Goochland Terrane. Additional evidence for a non-Laurentian origin for the Goochland Terrane comes from geochronology. So in 2010, Owens and others used uranium-lead zircon ages and found a crystallization age of about 403 million years old during the Devonian for some of these rocks in the Maiden's gneiss. Additional data from Chevelle and others in 2004 shows a Devonian crystallization age for monazite as well, again indicating that perhaps not all of the terrain is actually of Laurentian origin. So the most recent map that we have of the Goochland Terrane is the 1993 state map put together by the Virginia State Survey. And here we have the three State Farm gneiss domes that Farrar first observed. But what we don't know is actually the extent of the North Anna Dome, which is where I'll be talking about for my research. And so due to the coverage of the coastal plain in the area, it makes it difficult to find outcrops of the North Anna Dome, and therefore it's difficult to understand its full extent. So the purpose of my research is twofold. I hope to understand the structural geometry and deformation kinematics in the northeastern Goochland Terrane. And to do this, I will use uranium-lead, uranium, thorium, helium, and argon-argon geochronology to determine the deformation and metamorphic history of the terrain. And hopefully, by completing these two goals, I can determine whether or not the Goochland Terrane is Laurentian or Gondwanan in origin. So for my fieldwork for this research, I did two traverses, one along the North Anna River, starting from the Spotsylvania zone, going into the Hyla zone. And then I also went to the U.S. Silica Quarry in Montpelier, Virginia, to take samples of the Montpelier anorthosite down here. This here is a generalized geologic map with structure data that we've collected. So this data is compiled with measurements from Weems in 1985 and Latan in 2016. And the data was primarily collected along the North Anna River, the Little River, and the Newfound River to the south. And we collect these samples, or these measurements along rivers, because that's where we tend to have the best outcrop of these rocks. So now I'm going to walk through, going from west to east, in this figure, the different rock types that we see. So this here is an outcrop of the Maiden's gneiss. This is a politic gneiss that has a kyanite K-spar assemblage in spots, indicating that this rock experienced high pressures and temperatures. So this is starting over here in the west, right about here. Moving towards the east as we get into the core of the State Farm Gneiss Dome, this is outcrop 18HD3, which falls right about here. And this is the granitory gneiss that we know to be about 1 billion years old. And it has large garnet porphyroglass, as you can see here. As we continue to move east, we get into the Hylas zone. And previous workers have mapped the Hylas zone as a monolithic mylonite zone. However, we see that that's not really the case when we look at it in the field. It's actually a zone of variably mylonitized felsic and mafic rock. And so here we have an example of a felsic rock that we see in the Hylas zone and a mafic rock. And as we move towards the Fort Church Fault here, which is the border fault for the Taylorsville Basin, we get a felsic mylonitic gneiss, which comes from right about here in the Hylas zone. And finally, once we move past the Fort Church Fault, we get into the Triassic Taylorsville Basin, where we see conglomerates and other sedimentary rocks. So now we'll take a closer look at the structure data that we've actually collected here. So this stereogram shows the poles to foliations from the northern portion of the North Anna Dome. So all of these measurements that have been collected along the North Anna River. And where these poles plot, they suggest that we have a shallowly dipping foliation that dips to the north, and we know that this foliation is also folded. If we now look at the southern portion of the dome from the data collected along the Newfound River down here, we see that these poles to foliation suggest a shallowly dipping foliation to the south, and again, this foliation is also folded. In addition to foliation measurements, we also have lineation measurements for these minerals. And these lineations are mostly trending north-south, which suggests that they formed during some origin parallel elongation, which is also likely when these dome structures were formed. It's also helpful to visualize this in cross-sections so we get a 3D look of the terrain. And starting from the northwest with the Maiden's Gneiss, here we then move into the State Farm Gneiss Dome. We get to the Hylas Fault Zone where we have more relief. And then finally, the fall zone of the North Anna River, leading into the Taylorsville Basin with the Fort Church Fault bounding it to the west. So now I'll talk a little bit about the geochronology methods. So as Chuck mentioned, we went to the University of Texas at Austin last summer to use their UT Cron laboratory to perform uranium lead and uranium thorium helium analyses for these minerals. So we use standard mineral separation techniques that I'll talk a little bit about up next. These grains were then mounted on low lead tape in depth profile using a laser. So this is an example of what it might look like, where you have a zoned zircon and the laser has cut into the grain so we can get both core and rim ages. These analyses were performed using a laser ablation inductively coupled plasma mass spectrometer, and it's a photo machine analyte laser with a thermoelement mass spectrometer. And the second and tertiary standard uncertainties that we have is less than 2%, which is very good. So as for the mineral separation techniques, we flew to Texas with about 165 pounds of rocks, and then we crushed them using this jaw crusher, as Kinsey's demonstrating here. From here, we took the smaller fragments and put them in a disc mill pulverizer to get a fine sand. And we then took the sediments, which we have here, and put them onto a water table. And so the water table will separate out water table lights and heavies based on density. And from here, we take the water table heavies, put them through a round of heavy liquids, so bromoethylene, and then that helps to separate the minerals by their density. And then from here, we take the heaviest minerals from the first round of heavy liquids, put them through 4 rounds of the magnetic separator, and then we take the highest non-magnetic fraction and put it through another round of heavy liquids to further separate the minerals by their density. And again, we put it through another round of the magnetic separator for 4 rounds, and then the highest non-magnetic fraction is where we find the zircons to actually date. And then we're finally ready to pick and mount the grains. So zircon is an igneous mineral that forms during the crystallization of magma, and as we saw on the previous slide, we can have cores and rims in a zircon. So this zircon right here shows the core and then rims, which have formed during subsequent metamorphic events where the grain has experienced partial remelting. And when these grains crystallize, they have a small amount of uranium in the crystal lattice. And over time, this uranium decays to lead. And so we use two different isotopic systems, uranium-238 to lead-206, and uranium-235 to lead-207. And so these two systems have different half-lives, and ideally, when we use both systems to date a grain, the ages will be concordant, and the data will hopefully be good. This is now an example of all of the minerals we could date in a rock. So this is a sample of the State Farm gneiss. So I'll only be recording uranium, lead, zircon ages today, but we also have uranium, lead, rutile ages that we're rating on, argon, potassium, feldspar, and biotite, and then uranium, thorium, helium for apatite and zircon. And all of these temperatures here are the closure temperatures, and that's the temperature at which the decayed product will be fully retained within the crystal lattice, and therefore we can compare the parent to the daughter ratio to determine the age of these minerals. I'll now start walking through my results going from the oldest rocks to the youngest rocks. So we'll start with the State Farm gneiss. This is an outcrop of the State Farm gneiss on the south side of the North Anna River from the center of the North Anna Dome. And you'll see a well-defined foliation here with these nice pegmatite ludens that preserve a top to the south-southwest sense of shear, as we can see. If we take a closer look at the structure data collected at this outcrop, these are all of the foliation measurements that were taken within the State Farm gneiss dome. So outcrop 18HD3 falls right in here, and all of these foliations are very shallowly dipping towards the north-northeast and then to the east on the eastern side of the dome. So at this outcrop, we see two varieties of the State Farm gneiss. One that's a more fine-grained variety with biotite forming foliation, and some small garnet porphyroblasts that are a little difficult to see. This is what this rock looks like in thin section. So on the left, we have a full scan of this thin section. You can see these small garnet porphyroblasts here that have some inclusions. We also have quartz ribbons, plagioclase, biotite, and up here on the top right, this is an example of what a zircon might look like in thin section. And so the rainbow colors that are around the perimeter of the rim are a pleochroic halo. So there's been some release of uranium that has actually damaged the surrounding biotite grain that's seen here, and therefore it leaves behind this kind of rainbow appearance. Down here we have an example of what one of the garnets would look like. This is in plain polarized light, and you can see it has several inclusions within the actual grain. We'll now look at an example of the coarse grain fraction observed. So this is the 18HD3B, and we have these large garnet porphyroblasts that preserve these biotite tails as well. And the biotite and garnet are within the plane of foliation. So the foliation that we see in this rock is broadly parallel to the short axis of this thin section. This is another example of what the garnet might look like. So as you can see, there are several inclusions. And then down here on the bottom right, another example of what a zircon would look like in thin section. There just so happen to be a nice little cluster of them that actually look quite euhedral, which is kind of the typical shape that you would expect for a zircon. So now looking at the geochronology that we see for the State Farm gneiss. These 49 ages came from 40 individual grains because we have some that yielded both core and rim ages. And we broadly have two populations, one that goes from 1 billion to 1.2 billion years old, and one from about 250 to 350 million years old. So we can also visualize this as a core rim plot. And when we look at this in a core rim plot, we see that most of these single ages in some of the cores are falling between 1 and 1.2 billion years old, which aligns with previous work that suggests the State Farm gneiss is from the Grenville orogeny magnetism. And then we can also look at these rim ages and a couple of the single ages to see that they're falling around 300 million years old, which suggests that these were perhaps reset during the Alleghenian orogeny. So in summary, for the State Farm gneiss, we have a Grenvillian crystallization age with Alleghanian metamorphic overprint. Next up, we have the Montpelier anorthosite. So in 1996, Aleinikoff and others got a crystallization age of about 1.05 billion years old. And so here, this is at the U.S. Silica Quarry in Montpelier, Virginia. And most of the anorthosite that we see is very fine-grained. It's been metamorphosed. But we do have lenses of a coarse-grained anorthosite that kind of go through the middle of the quarry. And then this has been cross-cut by Jurassic-aged diabase dikes that are broadly striking to the north-northwest. This is taking a closer look at the western pit of the quarry, and we can see the foliation that's gently dipping to the north, and this is our view to the west. So now we'll take a closer look at the rocks that we actually find in this quarry. So on the left, we have an example of the coarse-grained anorthosite. So anorthosite is typically at least 90% plagioclase, and in both cases, the plagioclase that we find in these rocks is andesine. And so on the left, we have the coarse-grained anorthosite. On the right, we have two examples of the finer-grained myelinitic anorthosite. And so on the top, we have 18HD7, where we have these rutile porphyroclasts that are within the plane of foliation. And on the bottom here, we have plagioclase porphyroclasts that preserve a sense of shear as well within the plane of foliation. Taking a look at these rocks in thin section, this is 18HD7 with the rutiles. And so we'll see these rutiles also have tails similar to how garnet had biotite tails that we observed in the State Farm gneiss. And during some metamorphic event, we started to see titanite growing at the grain boundaries of these rutiles. Additionally, we can see the tail of a rutile grain here within the foliation. If we look at 18HD11, this is the one that has plagioclase porphyroclasts within it, we have these two beautiful grains of perthite that are preserved. And most of this then is metamorphosed plagioclase with subquartz ribbons and opaque minerals that are forming within the foliation. And here's an example of what this perthite looks like up close with its grain boundary. So when we look at the geochronology with the uranium-lead zircon ages that we've obtained for the Montpelier anorthosite, we have a few populations. One that's around 1 billion years old, which would align with what previous workers have gotten as a crystallization age. Another one from about 600 to 675 million years old, and one from about 275 to 375 million years old. And we interpret this older population to have to do with the crystallization of the Montpelier anorthosite, the 600 to 675 million year population to correspond with the emplacement of those granitic plutons within the Goochland Terrane around 630 million years ago, and this younger population to correlate with the Alleghanian orogenate. So in summary, in this rock, we have a crystallization age around 1040 to 1060, the effect from the 630 million year old granites, and Neo-Akkadian to Alleghanian metamorphism and deformation that likely formed the foliation that we observe in these rocks. So now we'll move into the Maiden's Gneiss group. And so this is the rock that has a kyanite potassium feldspar assemblage in places. And so this is outcrop 18HD1. And what we'll see here are what look to be these oval, oblong shapes that perhaps might be the eyes of sheath folds. And so sheath folds can form when you have a fold, and then the fold axis starts to migrate relative to the overall structure. And over time, as these are eroded, we then get left behind with these eye-like shapes. This is the view to the west of that same outcrop where we can see these fold hinges that have been refolded over time and cross-cut by veins as well. So this is a thin section from 18HD1, and we can see here that we have biotite and garnet that are forming the foliation here. We also have quartz, plagioclase, and most importantly, kyanite. So kyanite in this thin section is this yellowish mineral towards the top, And this is an example of what a kyanite grain would look like up close. So kyanite forms when a rock has experienced pressures of about 7 to 9 kilobars and 650 to 750 degrees Celsius. So these rocks were very deep and very hot, and perhaps are some of the deepest rocks that we've found in Virginia. Just upstream from 18HD1, we have another outcrop of the Maiden's Gneiss group, and it has a very similar assemblage. So plagioclase, quartz, potassium feldspar, garnet, biotite, and kyanite, most importantly. And so in thin section, this is what this rock looks like. We again have these garnet porphyroblasts that have biotite tails, preserving that sense of shear. And down here, you'll notice we have quartz with what is actually muscovite surrounding it. So the presence of muscovite in this rock indicates that it may have experienced more retrogression during an additional metamorphic event than 18HD1 did. And up here, we have another example of a garnet with biotite tails, and down here, a fractured kyanite grain from this rock. So now if we look at the uranium lead zircon ages that we've obtained for 18HD1, we have two broad populations. One that spans from about 725 million years old to about 1.7 billion years old. And then another that spans from about 360 million years old to about 475 million years old. And so when we visualize this as a core room plot, again, we can see that there's a pretty broad population and then a cluster around 400 million years old. So we interpret this older population to be a detrital source. So the protolith for this rock was originally a sedimentary rock, and then it experienced some metamorphism corresponding to the Akkadian orogeny that left us with these rim ages. So in summary, this is a palitic protolith that was deposited between about 500 and 725 million years ago that was sourced from much older rocks, and then it experienced high-grade metamorphism during the Akkadian orogeny, which is also possibly what formed the sheath folds that we see in outcrop. We'll now take a look at the high strain zones that bound the Goochland Terrane to the west and to the east. So starting at the west, we have the Spotsylvania high strain zone, and this is a granitic gneiss that has been intruded by a granite pegmatite, which was then deformed and has left behind these small porphyroclasts that preserve a sense of shear. When we look at the uranium lead zircon ages for the granite pegmatite in the Spotsylvania high strain zone, we can see a population from about 400 to 475 million years old and 300 to 375 million years old. And so it's possible that this granite pegmatite intruded during the Taconic orogeny and then experienced additional deformation during the Alleghenian. So we have the intrusion of the granite pegmatite somewhere between the Taconian and Akkadian orogenies and additional deformation here. Now moving into the Hylas high strain zone, which bounds the Goochland Terrane to the east. This is the zone that's been previously mapped as a monolithic zone of mylanites, but as we'll find out in a second, that's not at all the case. So I collected two different samples from this region, HD4 and then 27 TB, and this is at the falls of the North Anna River, just west of the Fort Church Fault here, which is a normal fault bounding the Triassic Basin, this Triassic Taylorsville Basin to the west. So we'll start by taking a look at the outcrops of HD4. So on the left here, we have an example of an outcrop of hornblende gneiss at 18 HD4. And you'll notice the well-defined foliation and some folding that has occurred here. On the right is another hornblende gneiss with 18 HD4B. And we'll take a closer look at this thin section. So in thin section, we can see a hornblende here that's broadly forming foliation, plagioclase and quartz as well, and then fractures here that are broadly parallel to the short axis of the thin section here. So here's an example of one of these fractures up close, and then an individual plagioclase grain that's been deformed. Sample 18HD4D was taken about 10 meters from 18HD4A and B, and it looks very different. We see potassium feldspar, porphyroclast, quartz, and most notably pseudotachelite veins that cut this outcrop. And so in thin section, we have these veins of pseudotachelite, and then a bunch of monkey business with some quartz and plagioclase as well. And so the presence of pseudotachelite veins indicates that this rock experienced a lot of brittle deformation. So we are in the fault zone, which makes sense. And now we're going to look at VA17027TV. So this is the outcrop that's closest to the Fork Church Fault, and it's a felsic mylanitic gneiss that has several porphyroclasts here. And we'll take a closer look in thin section. So we have a lot of quartz and plagioclase in this rock, and opaque minerals as well, and these quartz ribbons that are foliation forming. So when we look at the uranium-lead zircon ages that we have obtained for this felsic mylanitic gneiss, we have kind of one large population going from 225 million years old to 525 million years old. So absolutely no signature older than the Paleozoic. So we interpret that the protolith for this mylanitic gneiss crystallized in the early Paleozoic around 500 million years ago. And then the rock experienced additional metamorphism and deformation during the Akkadian and Alleghenian orogenies from 300 to 400 million years ago. Now to get into some interpretations for this data. So we'll start with the State Farm gneiss. And on the right here we have a probability density plot. So this plot uses the best age and the 2 sigma error to determine the relative probability that a grain is of a certain age. So up top with the State Farm gneiss, we see that the ages fall broadly within the Grenville magmatism, which we expect, with another pulse around the Alleghenian orogeny. So we have Grenvillian crystallization and metamorphism. We also know that it's comprising the center of these domes that we've observed in the Goochland Terrane, and it is structurally below the Maiden's Gneiss group. Now to take a closer look at the Montpelier anorthosite. So we interpret it to have a Grenvillian crystallization and metamorphic age, and we know that it comprises the center of a dome within the State Farm gneiss, where we see it in outcrop, and it experienced additional metamorphism and deformation in the Alleghenian orogeny, and it is also structurally below the Maiden's Gneiss group. Now moving into the Maiden's Gneiss group and the Hylas zone. So when we take a look at the probability density plot here, we see the broad population of the Maiden's Gneiss with really no strong Grenvillian signature, and a correlation with the Alleghenian orogeny, the Akkadian orogeny, but not so much the Alleghenian orogeny. And when we look at the Hylas zone, we have absolutely no signature from the Grenvillian orogeny, but correlation with Akkadian and Alleghenian deformation. So we have no significant Grenvillian signature. We also know that the rocks in the Maiden's Gneiss group experienced high pressures and temperatures that were responsible for forming the kyanite and potassium feldspar assemblage, and we know that these units are structurally above the State Farm gneiss. So now if we zoom into the probability density plot, looking just at the Paleozoic to get a better idea of these age relationships, again, with the State Farm gneiss, we see an Alleghenian signature, as we do for the Montpelier anorthosite, only an Akkadian signature for the Maiden's Gneiss group, and then moving into the Hylas zone, we have signatures from the Akkadian and Alleghenian orogenies. So with this, we propose a new stratigraphy for the Goochland Terrane. So starting with the Laurentian basement rocks, we still observe the State Farm gneiss, the Montpelier anorthosite, and the 630 million year old plutons that have intruded, and that comprises what we're calling the Laurentian basement sequence. And then, as for the cover sequence, we interpret it to be of Gondwanan origin. So this now comprises the Maiden's Gneiss group, the Savin amphibolite, and the Hylas zone, felsic and mafic gneisses, due to their relatively young age. So if we have a tectonic contact between the cover sequence and the Laurentian basement rocks, then the State Farm gneiss domes that we observe in map view are in fact tectonic windows as indicated by these teeth on the domes. And so these domes are then framed by thrust faults. And so with this, we proposed a new map for the Goochland Terrane. Going from west to east, we still have the Chopolomsik Terrane, the Spotsylvania Fault Zone, the Goochland Terrane, but what's most different about our map is that we don't have the North Anna Dome extending as far south as they do on the Virginia state map from 1993. And this is where the Montpelier Anorthosite is, and we interpret that these three domes in the Montpelier Anorthosite are all tectonic windows. So in summary, we'll start with the Laurentian rocks of the Goochland Terrane. We have 1 billion-year-old State Farm gneiss, and its protolith was emplaced around then, along with the Montpelier Anorthosite, and then 630 million-year-old A-type granites intruded these rocks. As for the Gondwanan portion of the Goochland Terrane in our cover sequence, between 500 to 725 million years ago, we had the deposition of the Maiden's gneiss group protolith, and then around 500 million years ago, we have the crystallization of the protolith for the Hylas zone, and then 400 million years ago, these rocks experienced some high-grade metamorphism and deformation during the Acadian orogeny. And finally, we have the Goochland Terrane united. And so the suturing of the Maidens and Hylas rocks over the Laurentian basement rocks likely happened during the Neo-Acadian orogeny. And finally, once they're both together, they were translated to the southwest during the Alleghenian orogeny, and that's also when these dome structures were formed. And finally, they were during Atlantic rifting and the formation of the Triassic basins, the Goochland Terrane was exhumed. So some conclusions from my research. We know that the North Anna Dome is a doubly plunging antiform in the Goochland Terrane, and we have uranium-lead zircon evidence that suggests there's no common history between the State Farm gneiss and the Maiden's gneiss group prior to the Alleghenian orogeny. We know that these domes are bounded by faults, and as such are tectonic windows in the terrain, and we interpret it to be a cryptic suture that placed Gondwanan rocks over top of the Mesoproterozoic Laurentian crust. And then finally, there was likely a Neo-Acadian suturing of the Goochland Terrane. So as for future work for my research, we'd like to obtain additional uranium-lead and uranium-thorium-helium ages from the UT Cron laboratory. And so we have some uranium-thorium-helium zircon ages already, but we're also hoping to get uranium-lead and uranium-thorium-helium for both apatite and rutile in some of these rocks. We also are in the process of getting argon-argon ages for biotite and muscovite, potassium feldspar and amphibole for several of these samples. And by getting these low-temperature thermochronometers, we can hopefully reconstruct an exhumation path for the entire Goochland Terrane to better understand how it came to the surface during the rifting of the Atlantic Ocean. And we'd also like to closely study the contact between the Maiden's gneiss group and Laurentian basement rocks to better understand its origin. Lastly, I'd like to acknowledge Zachary Foster Barrell, Megan Flansburgh, Danny Stockley, and the rest of the UT Cron Laboratory for hosting us for 2 weeks last year and processing all of this data that allowed this project to be possible. Also, Ryan McAleer and the United States Geological Survey. We've been working with them for argon-argon ages for some of our minerals. The William and Mary Charles Center and the English Stonehouse Fellowship for providing funding to make this possible. And the students, faculty, and staff in the geology department for providing unending support throughout the last year and a half that I've been completing this research. So with that, thank you.
Okay, well, Hope is eager to entertain questions.
The image can an image there. I'm sorry. Yes, I'd be happy to take any questions. Caroline.
I was wondering if you could go back to the probability plots real quick. Can you explain the y-axis of that a little bit more? Because it's percent probability, right?
Yeah, so this is showing the percent probability that a grain is of a certain age. So to calculate that percentage, we looked at the probability, or the histograms that we also compiled for this data, and looked at how many grains were of a certain age at that point to determine the relative probability using the 2 sigma error.
Okay.
Yeah. Yeah. Musa.
In some of your core rim plots,
Mhm.
the core and the rim were really close,
Mhm.
whereas all the other points had one in the core, or one at about a billion years, and then one at 400. Do you know what's causing some of them to be really close together?
It's possible that some of them are discordant. It also, the core rim determination comes from the algorithm that the machine uses at Texas. And so basically the machine goes in and it says, is this a core and a rim age from this one grain? Maybe it is. If so, we'll identify it as that. So it's possible it's also something with the algorithm that's just misidentified an age. Yeah. Becky?
So I'm used to thinking about grain light ages for volcanic zircons, and so I wonder if you could explain a little bit with these metamorphic, the ages related to metamorphism. Is it that you have overgrowths on, so you're growing new zircons? So it's not so much like a thermochronology thing, but it's actually you're growing more zircon. Is that?
Yeah, so there's been some kind of partial melting during an event that has reset the rim of it and created a new zone. That makes sense.
Yeah,
So then we
I
get
was
the
wondering
zones
about
with the core.
resetting the age of a crystal that already exists, or new growth of the crystal.
New growth
Okay.
of rims.
That's easier to understand.
Yeah.
So if you were to be parachuted into the Goochland Terrane without a geologic map, would you come up with the same map units? I guess another way of asking it is would the geologic maps that exist, were they a help or a hindrance in the work that you were doing?
Absolutely a help, because we had an idea going in what we would expect to see. But again, a lot of these map units were kind of lumped together because we don't see, the State Farm gneiss does not look the same everywhere you go, just as the Maiden's gneiss does not look the same everywhere you go. So having the maps was definitely helpful, but we also have to acknowledge that there are varieties of these units that we can see in outcrop.
So if you have a unit that's not the same everywhere you go, how do you deal with that?
I mostly relied on previous work that had been done in the terrain, looking at the different rock types that we actually see outcropping, reading a lot of papers to see what other people have observed, and seeing if that aligns with what I'm also observing, and therefore identifying the outcrop as, say, the State Farm gneiss.
So if you have the State Farm gneiss in one place and the Maidens in another, are there places that you, excuse me, go in one or the other and say, boy, this State Farm looks more like the Maidens than it does State Farm, or vice versa? Did that ever happen?
That definitely happened with me. It helped that I was with people who had been studying this area for a long time and perhaps were more knowledgeable than I was in terms of discerning between the two.
So it's not always evident just walking up to an outcrop. You have to have some geographic reference
Yes.
or something like that. So one other question is the big bounding faults. I guess the model generally is that there's some kind of thrust faults.
Right.
Is there any sense that are they more thrust or are they more a strike slip? So I know you get farther north, like in Delaware, and these big bounding faults are basically huge, or interpreted to be huge strike slip faults, where basically on the east side, things have come from the north to the south, and on the west side, there's not been as much movement.
Question for clarification, are you talking about the bounding faults between terrains?
Yes,
or-
between
okay,
terrains,
Between
yeah.
terrains?
Yeah.
So the Spotsylvania zone tends to preserve, or I guess strike slip, dextral transpression type evidence that happened during the Allegheny and orogeny. But the Hylas zone perhaps might be strike slip as well, but we interpret there to be some kind of thrust fault that actually was responsible for placing the Gondwana crust over the Laurentian crust. So does that answer your question? Maybe?
Yes.
Yes. Okay. Brian?
What do you hope to find, or what do you hope to reveal with those new ages that are coming through? Are they just going to be more clarification onto your current results, or do you think that there's potentially like more to be discovered with those ages?
I'm hoping that with the lower temperature ages, we'll get a sense of like deformation that's occurred in the upper about 5 kilometers of the crust. So the uranium-lead zircon ages are mostly to understand the crystallization of metamorphic history, but these low temperature ages from the uranium, thorium, helium, and argon can help us understand brittle deformation that's occurred, and also the rates at which the Goochland Terrane was exhumed. So by getting a suite of argon ages across the traverse, we can then reconstruct rates of exhumation for the Goochland Terrane. Any other questions?
Okay, well, let's thank Hope one more time. So the general audience can head off to other places.